Ottawa, and they lost all their power right when I was finishing high school. And it, because a bunch of ice formed on all the power lines and it took them all down. It was kind of funny when we started dating. It was interesting going back to where her parents lived because there were no trees that were, much larger than I was, right? Because all the trees came down because it was this tremendous ice storm. So
Hopefully that won't happen again anytime soon.
hopefully not. You never know. You never know, right? Mother Nature's always got surprises for us.
Right.
So thanks for coming back, right? We've been talking about processes, right? So thermodynamic processes. We started talking about closed processes, right? That was the first kind of module of the course. Then we looked at open processes, right? Now we've been talking about sort of ideal versus real processes, right? This ideal or reversible process, they don't exist, but they do serve as kind of a measuring stick, right? Or an ideal that we can work towards. So you can never achieve this reversible process, but it does sort of set the limit of what's possible. So, we talked about before, and we'll go through an example today where you might not think when you calculate your thermal efficiency of your heat engine that you're doing all that well, but you can't be comparing that number to 100%. You have to compare it to the ideal or the Carnot efficiency, which we'll talk about today. Right? We've been talking about the second law and how ideal processes are processes where that sigma dot or entropy generation rate term is zero, right? And that's the best that can possibly, that's the thing that we can approach but never achieve, right? That's the limit of what's possible. But real processes, which are irreversible, they have things like irreversibilities, things like friction that are causing energy losses, right? And that is represented in the second law by this sigma dot term being positive. So anything that can happen in real life has a positive entropy generation rate. In the last class, we talked about how that doesn't necessarily mean that the specific entropy of the working fluid in your system is increasing, because you have to think about the entropy of the whole universe, and that includes also the entropy that's sort of accounted for in that heat transfer term. And we talked about the potential difficulties with that heat transfer term, that that you need to use the right heat transfer term. So it's the heat transfer term, same one you would use in the first law. But remember, it's Q dot over T. There's two things you have to remember about that temperature. The first is that it's the temperature outside of your system, right? And the second is that it's going to be a temperature, because it's not a temperature difference, so it's got to be in Kelvin or in Rankine. So we talked about this idea of thermal efficiency, which we'll explore a little bit more today. This is this idea that when you have a heat engine, what you're trying to do is you're trying to turn that input energy, which is heat, you're trying to turn that into another kind of energy, which is mechanical power, right? When we think about power plants, right? This is a spinning shaft that's attached to an electrical generator. And the question is, how much of that input heat energy actually made it into this mechanical energy, this spinning shaft? So that we can look at that. This is actually W dot net over Q dot in. But because if we do a first law analysis on the whole system, we can transform that into 1 minus Q dot out over Q dot in. I can show you that when we do the example today, right? So this is going to be some number less than 1, right? Because Q dot in is the biggest number in the problem. And Q dot out, remember Kelvin and Planck told us, yeah, you can have a heat engine that's going to run for long periods of time in a cycle, but you have to cool that engine, otherwise it's going to fail, right? And like I said, unfortunately, sometimes we see that on the side of the road where somebody's, pouring a, water bottle over their engine because they lost their radiator fluid or something. Right now, there's a special case here. So this equation, we can always use, this should say real and not ideal, right? But for ideal processes, right, we can make this substitution that a ratio of heat transfer rates can be replaced with a ratio of temperatures, right? So here we can then get the Carnot efficiency or the ideal efficiency as 1 minus T out over T in, or if you prefer, because where you're rejecting heat, that's the cold place, and where you're adding heat, that's the hot place, right? So that you can replace the outs and ins with colds and hots, respectively, right? Now, again, these are not temperature differences, right? So these temperatures, they have to be converted to absolute temperature. It's got to be Kelvin or Rankine, right? Cannot be Fahrenheit or Celsius, right? But you see, the cold temperature is going to be something that's, higher than absolute zero, but lower than the cold temperature. So this is going to be 1 minus some fraction that's less than 1. So our thermal efficiency has to be something between 0 and 1. We also talked about this idea of coefficient of performance, that we can use a similar methodology to look at devices that kind of work in the opposite direction as heat engines. Heat engines were putting in heat and we're getting out work. Whether you're talking about a heat pump or a refrigeration cycle, the input is the work, right? You plug your air conditioner into the wall, and the energy benefit, the thing we're trying to do, is move heat either out of the cold place or into the hot place, right? So we're trying to move the heat in the opposite direction that it would go normally, right? Now, you can remember, if you want, which Greek symbol goes with which. So for heat pumps, we use gamma, right? And for refrigerators, we use beta. But if you want, you can always just write COP, that's coefficient of performance. The way that I remember this, right, is refrigerator starts with the letter R. And if I squint enough, beta kind of maybe looks like an R, right? It certainly looks more like an R than gamma does. So that's how I remember it. It's maybe not the best way, but that's what I do. Now here, because the energy cost is the net work, so this is going to be, you would start with Q dot hot minus Q dot cold, but then we're making the Carnot assumption here, so these become temperatures. But so this is the work term, and then the heat pump, the energy benefit is heating up the hot place, so we put in the hot temperature here on the top. In the refrigerator, the benefit is cooling down the cold place, so we put the cold temperature on top. So that's kind of just an overview of what we did last class. Right? Now today, we're going to sort of start to put this in practice. We're starting to put all the pieces together, right? And this is what we're going to be doing basically for the rest of the class. Certainly as we get past the second midterm, we're going to start to look at cycles, right? So I've been kind of making this promise that what we're going to do in this class, really cool, because we're going to start to look at like nuclear power plants and coal power plants and airplanes and all this cool stuff. And the way that we do that is by analyzing cycles like this, where we stack a bunch of thermodynamic processes together in series, right? So this is a, I guess the most basic version of a coal-fired power plant, and it's got 4 different components, right? So remember, it's a heat engine, so we got to add heat. So here's where you're actually burning the coal, right? But there's this tube, right, that's got water in it, right? And we're adding heat from this burning coal, and it's boiling this water, right? It's making it water vapor. And that water vapor then goes into a turbine because, right, we know that there's this, factor of 1,000 difference between the specific volume of liquid water and steam, right? So the steam wants to take up lots more volume than the liquid water. So it wants to expand. So it kind of rushes out this tube, right? And that's the whole benefit of this system. The whole reason people came up with this system is they figured this out, that the steam will want to rush out here. So they put on a spinning shaft, right? So this is on bearings, right? So it spins easier. And there's fan blades here, kind of like what you'd see in a wind turbine, right? And because this steam is racing through this turbine over these fan blades, they're designed in such a way that that's going to create torque on this shaft, and the shaft is going to spin, right? So this turbine, this is the whole reason that we want to run this kind of a system, is because we're trying to get this mechanical work. We're trying to get this spinning shaft, right? And then we make friends with an electrical engineer, we hook it up to an electrical generator, and we put power out onto the grid. Now, we got to get back to the same thermodynamic state that we had when we went into the turbine. So what do? Now we have steam, but its pressure is low, right? So what happens is we cool that steam down back to a liquid, right? So that's why you see those, like in The Simpsons, they got that, it looks like a smokestack, but it's not really a smokestack. What happens is steam comes in the bottom, right? And that steam wants to rise, and then it cools, right? And then as it cools, it condenses, and then it rains back down into, a pumping system that's at the bottom of that stack that pulls water back into the system, right? So we condense that liquid water, but it's still at low pressure. We need high pressure steam over here. So this is still at low pressure, so we run it through a pump to get it up to high pressure. That doesn't take much work. That takes much less work than the work we produce. And then this high pressure liquid goes back into the boiler where it turns back into steam. Now it's high pressure steam, goes through the turbine, and we generate power. And we kind of keep, so these same water molecules or fluid elements just keep running round and round and round and around, right? And that's why we call this a thermodynamic cycle, because the same group of water molecules keep running around and around and around the system, right? In this cycle, or a circle if you want, right? So what we're asked to do is find the thermal efficiency of this system, find the Carnot efficiency of this system, and I'll also go through how we draw a TS diagram for this whole cycle, because that's going to start to be important for us. Now, I won't do that in PowerPoint today. Today we'll go through this just in Word, right? So you'll see me actually work through the problem. Right, so this is the same information. We know some stuff here, right? So here I've got a state table with some information. I look here, I like state 1 because I have 2 independent intensive properties. Temperature and quality are always going to be independent. State 4S, I like this one too because it's also going to be 2 independent intensive properties. So I know I could fix those 2 states, but I got 4 states here, right? So for now, let's just say that I look at this like it's an exam. I look at this and I'm like, oh my, I have no idea how to fix these states. But that's okay. Dr. Scherzer told me, if you don't know what to do, try to solve it symbolically. So we'll go through this symbolically first, right? And I guess first we'll draw the TS diagram, because then maybe that'll help us figure out what to do with fixing the states too. Then we'll get equations for the thermal efficiency and the Carnot efficiency. And then if we have time, we'll fix the states and we'll get numbers, right? Now you can find those same numbers just in the lecture online. I think even in the Thermo Short, I have all the data there. So if you want to spend 10 minutes, if we don't get enough time, you can check that out too. 5 minutes if you run it at a higher speed, right? So the first thing we want to think about is, what are the governing equations, right? So these are all the governing equations that we kind of know for open systems and cycles, right? So here we have conservation of mass, conservation of energy. We learned about the second law. We know something about thermal efficiency now, and Carnot efficiency. One thing that maybe I didn't mention yet, right? So oftentimes when we don't have enough information on the state table to find everything, there's something about the process information that we know, right? So here there's a bit of a hint, because this says 2S and 4S, which suggests to us that they're isentropic. We'll go over what that means when we get there. But it also tells us that this is an ideal heat engine. So that must mean that for all processes, sigma dot is equal to 0. Because all of the processes, for the whole system to be ideal, it must mean that all of the processes have sigma dot being equal to 0. So we can start. Now, this is pretty common on an exam. You might be asked to draw a TS diagram for this whole system, right? So we'll start there. And I cheated a little bit because I already started here. So the first thing when we draw a TS diagram, the question we have to ask ourselves is, what's the fluid, right? And the reason we ask ourselves that question is because if it's water, or maybe some kind of a refrigerant where we're boiling it and condensing it, then we need to draw a vapor dome, right? But if it's an ideal gas, we don't draw a vapor dome, right? So here we know that the working fluid is water, so we have this vapor dome, right? Now from here, I can see that two of my states, state 2s and 3, are at 10 degrees, and two of my states are at 300 degrees. Right, so I've got my TS diagram, I drew my vapor dome, I can see, or maybe I just know at this point, which is fine, I think I cut off some of this table, but 300 is still on. This is a two-phase table. This is the same table basically that you would see in A2, but this is from the FE handbook, so it looks a little different, but it's the same table with temperature on the left, and 300 is on this graph. So that means we're not above the critical point. Right, so I know that 300 is over here, and 10 degrees is obviously less than 300. So, this is not to scale, right? It's just some sketch, but that's okay. So I know that I have these constant temperature lines here. Now, I could also draw constant pressure lines if I wanted to. So I could see that for 10 degrees, the pressure would be, this is in kilopascals, so 1.23 kilopascals we'll say. So this is a constant pressure line if I wanted this information. So this would be 1.23 kilopascals. That's not too surprising, right? Because we know that water boils at 100 degrees if we're at 101.3 kilopascals, right? So here, because water's boiling at 10 degrees, well, we must be less than that 1 atmosphere, right? Now, if I go down to 300 degrees, then this means that we're at 8.5. Oh, I think I cut off the header here. I think that this now becomes, sorry about that. I think I got it down here. This becomes megapascals once we're over 220. So I'll write that back up in my table. So this now becomes megapascals, right? So this is 8.51 megapascals, right? So here, if I wanted to draw this one, I could do this. So this is 8.5 megapascals. Right, which again makes sense. It's bigger than 100 kilopascals anyway, right? Now there's 2 points I can put on here for sure. So it tells me state 1, which is going into the turbine, right, is at 300 degrees and 1 quality, right? So I'm right on the red line. This here, this is state 1. Right? This is going into the turbine. The other state I know for sure is state 4s. So this is coming out of the pump, right? Is also at 300 degrees. And now it's right on the blue line. So here, as I go through the boiler, I can see that my process is going from state 4s to state 1. This is going through the boiler. So what we're doing here is we're adding heat. Now the next part's maybe a little bit tricky. So these next two states are both down at 10 degrees. But the trick here is that we are assuming, here, let's just quickly do a second law on the turbine. Right, so here we'd have ds by dt is equal to q dot over t plus the sum of m dot in s in minus the sum of m dot out s out plus sigma dot. So what do we know about this process? Right, we know that it's at steady state. We know for the turbine, we're going to say that it's adiabatic, that it's not losing any heat. So that Q dot term goes to 0. But the problem also told us that it was an ideal cycle. So all are ideal. So that sigma dot term goes to 0. We also know that it's one inlet and one outlet, right? Here, if I did mass conservation on the turbine, I would see that by dm by dt is equal to the sum of m dot in minus the sum of m dot out. I'm still going to say it's steady state because I can't make different assumptions for different parts of the problem if I'm talking about the same component. So this tells me that the mass flow rate in to the turbine is equal to the mass flow rate out of the turbine, which means there's only one mass flow rate, right? So then what this second law equation tells me, I'm running out of room a little bit, is that 0 is equal to, there's only one mass flow rate, times S in minus S out. But if the mass flow rate can't be 0, then that must mean that this part must be 0. So that means that S into the turbine is equal to S out of the turbine, right? Or that this system is isentropic, right? Isentropic means that the process has constant entropy. And that's what we mean when we say 2S, right? So here, this state, 2S, has the same specific entropy as state 1. So now I'm going to go from 1 to 2S. This is a vertical line down because the process is ideal. And then it was at steady state, adiabatic with one inlet and one outlet. And that means that the specific entropies must be the same. Now, what's the purpose of the turbine, right? The purpose of the boiler was to add heat. The purpose of the turbine is to produce power. So as we go from state 1 to state 2, we're generating power. I could do the same analysis here if I just wrote the word pump here. I could do the same analysis. The pump is also at steady state. We're going to assume that it's adiabatic, that has one inlet, one outlet, that it's ideal, right? And this same conservation of mass applies. So even though 4S, that's the outlet, right? That what we'd see is that state 3, S3 is the same as S4S. So this is also a vertical line. Here, we're going to be putting power in. This is W dot pump, W dot turbine, right? So here we're putting work into the system or power into the system. And then as we go through the condenser, which goes from 2S, sorry, this is state 3, to state 3, here we're going to be rejecting heat from the condenser. Now, just as kind of a practical thing, I'm setting this up for a reason as being all under the vapor dome. In a real system, you wouldn't want to do this. You'd want to push this condensation till you're all the way at a saturated liquid because you don't really want vapor bubbles in your pump because it's it's not good for the pump. So usually you'd have something here that sort of accumulates the vapor and doesn't let it get into the system, right? But here, you'll see at the end why we want to do this, that everything here is under the vapor dome, right? So now this is my TS diagram. You don't have to put the process lines here where the heat's going in and work's coming out and stuff, but I find that useful because it helps me to remember what the purpose of each one of these processes is. Does anybody have questions about how we built the TS diagram?
Why is the vapor bad for the pump again?
So because it's compressible, right? So you want like a kind of a nice even load on the pump. So when you get these compressible pockets, then the load kind of varies all over the place. Plus, if you have these bubbles that are in and you got your fan blade spinning around, it can cause damage to the blades in the pump, you know,
Okay.
the impeller. So
Okay.
that's my understanding anyway. Right, so here, right, we're running around and around in this cycle. And the reason we call this a cycle, right, is because the very first state that we look at is also the very last state that we look at, right? The beginning state in the turbine is the end state of the boiler. So now we did this, let's try to get at least a symbolic solution for the thermal efficiency, right? So now we need symbolic solutions. And we've already talked about a couple of these, right? So where are my control volumes? I have 4 control volumes, right? So that means I'm going to have to do different analyses, right? I've got the turbine and the pump. These ones are going to be interested in generating power. And I've got the boiler and the condenser, and those ones will be interested in heat transfer rates, right? So there's 4 different control volumes that we might have to look at here, right? Now, there'll be a different kind of suite of assumptions that goes with these different components, right? So this is why, I mean, sometimes a test problem will say like, you know, what are your assumptions right at the beginning? And sometimes it says track your assumptions throughout. And I'm always a big fan of tracking your assumptions throughout. That's why I tell you to start with the governing equations, because then it's very easy for you and for me to see what your understanding of the problem is, right? So now as we go to what happens to the mass, we would do this for all of the systems. We would say that dm by dt is equal to the sum of m dot in minus the sum of m dot out, right? But for all the components, are at steady state and one inlet, one outlet. So for every component, we will get the same answers. So all components will say m dot in is equal to m dot out. So here, if I just draw it, right? So here's the, I got my turbine here, right? A condenser, a pump, and a boiler. We've labeled these states 1, 2s, 3, 4s, right? So here, if I look at the turbine, the inlet to the turbine is the same as the outlet of the turbine, right? The mass flow rate here is the same as the mass flow rate here. But because these are chained together in series, the outlet of the turbine, so this is the turbine, this is the condenser, this is the pump, and this is the boiler. But the outlet of the turbine is the inlet to the condenser, right? And the outlet of the condenser is the inlet to the pump, right? So what this is saying here, what the turbine is telling me, right, from conservation of mass, is that m dot 1 is equal to m dot 2s. But what the condenser is telling me is m dot 2s is equal to m dot 3. And the pump tells me m dot 3 is equal to m dot 4s. And the boiler tells me that m dot 4s is equal to m dot 1. So all of these mass flow rates are the same. Do you see how that happens? Does that make sense? Right, so there's only one mass flow rate. So I'm going to drop the subscripts on the m dots from here on out. Right? So now what happens to the energy? So here, for our conservation of energy, we're going to have d E now by dt is equal to, this is a metric problem, right? So I've got Q dot minus W dot plus the sum of M dot in, H in minus H out. Oops, that's not how that goes. Jumping the gun here. Plus, this is V in squared over 2. There's no GC here because it's not an imperial problem. GZ in minus the sum of m dot out, H out, plus V out squared over 2 plus GZ out. So over here, well, I'm not going to skip too many steps, but we know that for the turbine and the pump, they're going to have the same assumptions. So for the turbine and the pump, they're steady state. They're both adiabatic. They're both one inlet and one outlet. And then we're going to say that the change in the kinetic energy is approximately equal to 0, which is approximately equal to the change in the potential energy. So this is going to go away, and this is going to go away. So then I know that W dot for the turbine is going to be equal to M dot times H in minus H out. But here I see the inlet to the turbine is state 1. So this is going to be H1 minus H2S. And I also know, so this is for the pump, it's also going to be that W dot pump is going to be M dot times H in minus H out. But the pump, the inlet is state 3 minus state 4. So here's one equation that I might want to use. Right? Here's what happened when I did the first law on the pump. Now for the, here, we'll cross this out for now. For the boiler and the condenser, we're going to look at it a little bit differently. Well, let's just do the boiler, because we'll see that's the only one we're going to need here. But if we have some time, I'll come back and show you what you might be able to do with the condenser. Right? So the boiler is over here, right? It's also going to be steady state. So the boiler is going to be steady state. It's not going to be adiabatic, right? Because the whole point is to generate heat, right? So it's going to be passive. There's no fan blades. It's also going to be 1 and 1, and it's going to be no potential and kinetic energy changes. So if I did the first law on the boiler, right, I would say dE by dt is equal to Q dot minus W dot plus the sum of M dot in H in plus V in squared over still metric 2 plus GZ in minus the sum of M dot out H out plus V out squared over 2 plus GZ out. But the assumptions I've made here are that it's steady state. The heat transfer term survives, but the power term goes away. We'll call this passive. One inlet, one outlet, no potential and kinetic energy changes. And now what I'm going to get is Q dot from the boiler is going to be equal to M dot times H out minus H in. Right? So that's, hopefully, we're starting to see that's the expression we'll often get if we make these assumptions and we're talking about heat transfer, right? But H out, so this is going to be M dot times H1 minus H. So H out was 1, state coming in was H4S. Right, so I wrote here, is the process possible? Because that's one of the other questions that we ask for these open systems. But we already did that part, right? When we were drawing our, when we're drawing this process, right? We did a second law analysis on the turbine and the pump to convince ourselves that the specific entropy here didn't change. So I think we've answered those questions pretty well, the open system questions that we generally want to know. But now we're going to go to, we still don't have what the problem actually asked us for, right? What are we trying to find? We want to find the thermal efficiency, and the Carnot efficiency. All right, so here I'm just going to give us a little more space here. See if this works. Right, so now we got to remember how to do thermal efficiency. We'll start with the thermal efficiency, right? So if I'm trying to find the thermal efficiency, right, all of these system characterization terms, they're always the energy benefit over the energy cost, right? So the energy benefit here, the reason that we run a heat engine is to generate mechanical power. Oops, net. So it's the net power generated divided by the cost is the heat, but not the net heat, just the heat in, right? And that's why I only had to do the first law on the boiler, right? Because if we took the net work over the net heat, the answer would always be 100% efficiency because the net work is equal to the net heat as long as we're at steady state. So what is the net work? There's two different work terms, right? There's the turbine, that's the power producer, and there's the pump. So what do we do with these two terms? I don't know, right? Do we add them together or do we subtract them? The textbook, this is tricky because there's not really a wrong answer. The textbook will tell you to subtract these two numbers. But the textbook will also tell you that power from a pump is m dot times H out minus H in. I tend not to like that, right? Because it's really telling you the magnitude of the pump power. So for me, when I'm finding the net power, I'm always going to add these things together. And the reason that I do that is because when I take these terms from the first law will deal with the signs for me, right? So the first law is going to tell me, I expect, that my turbine has positive power because that's work out, right? Work out is positive. The pump is putting work in and work in is negative. So I add these things together, and the way you check this to make sure you didn't mess it up is you look at your net power. Your net power has to be less than your turbine power because the pump is a cost. It's not a benefit. So if you add these two things together and you get a power that's bigger than your turbine power, it means that you messed up the sign somewhere. Right? Because your pump, you have to plug it into the wall. It's consuming power. And here we divide this by Q dot in. Now the good thing is, right, we actually didn't really know any of these things. But the good news is we don't have to know them, right? Or I guess the good news is because we could ask you a problem like this on the exam and start with this equation, right? But so to get these, right, you have to do a first law on all, or I guess on the turbine, the pump, and this is the boiler. That's where we're adding heat. But we did that already, right? So we know that the turbine power is m dot times H1 minus H2S, that's in minus out, plus the pump power is m dot H3 minus H4S. Right? Again, I'm expecting the turbine power to be positive and the pump power to be negative. The boiler, that's going to be m dot times H out, which is H1. That's going to be actually the highest enthalpy in the problem because that's high temperature, high pressure steam, right? Minus the inlet here was H4S. We don't know any of this stuff yet, right? The good news is we have a symbolic solution, right? The bad news is we don't know anything. But I guess we can simplify this a little bit because the mass flow rates are all the same, right? And we can factor the mass flow rate out of the numerator and the denominator. So to fix this, we're going to have to fix the states. Now, if you want the numbers here, you might have to go to the long version of the lecture, but I'll walk you through the process. So state 1, we know the temperature, and we knew that the quality was equal to 1, right? So this one is going to be Hg, and I believe that's at 300 degrees. But the other thing that I would get from this, right here, maybe I'll do the stuff in blue, the stuff you'd pull off the table. A2 if you were doing this from the textbook, right? So from here, you would get H1, but you'd also want to get S1. Right? Now, why do you want to do that? Because when you get to state 2, the only thing you actually know here is you know T2, right? But that's the only thing we know, except because we did the second law analysis, it told us that S of 2S is equal to S1. Right? Now, when we drew this, remember we were under the vapor dome, we were coming from like here down to here, so from 1 to 2S. We expect, now we're going to look at the row for this is 10 degrees Celsius. We expect we have SF, right? And we have SG, and we expect S1 to be somewhere in between here, right? S1, which is equal to S of 2S. So we want to find the quality for this state. So what we're going to do is we're going to use our quality equation to say that, well, X2S must be equal to S of 2S minus SF divided by SG minus SF. This will give us X2S, right? So in this equation, I know all of this stuff, right? This is the tricky thing here is this is evaluated at 10 degrees Celsius, not at 300 degrees Celsius. So this will give me X of 2S. Now, I get to use the quality equation again because here I'm going to say what I really actually want is H of 2S, and that's going to be equal to HF plus X2S HG minus HF, or if you prefer HFG, right? And again, this is all evaluated at this 10 degrees Celsius line, right? So now I know HF and HG from the table, but I had to get X2S from up here. Does that make sense? So now, right, when we look at this, now we know state 1, we know state 2S, we just need 3 and 4S. Here, we're going to start with state, I'm going to start with 4S, because that's the one that we know. Here we were told that the temperature was 300 degrees and that the quality was equal to 1, or to 0, I'm sorry. So this is saturated liquid, right? So here, now this is going to be very similar, right? We're going to follow almost the same process, but now S4S is equal to SF at 300 degrees, because that's the temperature for this state. And H4S is equal to HF at 300 degrees. For state 3, from the second law, well, first I know that temperature is 10 degrees. And the second law told me that, S3 is equal to S4S. So this is just like the process here. I'm going to find X3 is going to be S3, which is the same as S4S, right? Minus SF divided by SG minus SF, again at 10 degrees. And then I'm going to find H3 will be HF plus X3 HG minus HF, right? So I'm going to put this value into here. So again, it might be worthwhile to look at maybe the thermal short or the long version of this lecture that's posted in the lecture series YouTube playlist to go through the mathematics of how to do this. Or in my notes, I do it too that are posted online, right? But you can see how to actually fix the states and what the numbers are. But now I have all these values, right? And when I put them in, the equation that I got, or the thermal efficiency that I got, was, where are we? I'm still fixing the state. Sorry, I know this is very exciting. 50.6. So this was percent, or 0.506, right? Here, I would have had to multiply by 100 to get that number, right? Now, you might think that that's not so good, right? So let's compare this to the best possible performance we could get from this particular heat engine, right? So now we can go to our Carnot efficiency. This, again, is going to be net work divided by heat in, but we'll remember that if we're at steady state, that W dot net is going to be equal to Q in minus Q out, right? Or we could, I think it becomes a little easier if we start to talk about these as Q hot and Q cold, because we're going to put temperatures in here, right? So this becomes Q dot hot minus Q dot cold over Q dot hot. I can factor this around a little bit, right? And say 1, right? Q dot hot over Q dot hot is 1 minus Q dot cold over Q dot hot. This actually, you can do this. This is true for real processes too. But now here's the switch. For Carnot, or ideal processes, ratio of Q dots, Q dot over Q dot, can be changed into T over T. So my Carnot efficiency could be 1 minus T cold over T hot. Ideally, to answer this part of the problem, we would want to know the temperatures outside of our boiler and outside of our condenser. But failing that, because these things happen at constant temperature, we could imagine that the lowest maximum temperature is 300 degrees and the highest cold temperature is 10 degrees. So I'm going to still say that this is 1 minus 10 degrees Celsius over 300 degrees Celsius. But I got to remember, because these are not temperature differences, these have to be in absolute. So now I've got to add 273 to the top and the bottom. You'll notice that'll give me a very different answer, right? If I did, 10 over 300 is much different than 283 over 573, right? And you know what's interesting about this is that when I do this, I get 50.6%. right? So, this took us, I guess the rest of the problem took us half an hour. And this part took us 2 minutes, maybe 4 minutes, right? We got the same answer. We only got the same answer because we assumed that the process was ideal, right? So the good news about this is we learned sort of functionally how to analyze a nuclear power plant or a coal power plant, going, component by component. But when it's ideal, when the system is ideal, you can skip right to this, right? If ideal. So there's a couple questions about this, right? The first one is, man, this number's low. It'd be nice to get this number higher. We're going to learn how to do that, right? And I guess the next part is we're going to start to deal with what happens when the components are not ideal, particularly when we talk about turbines and pumps. How do we deal with turbines and pumps that are not ideal? But we obviously won't talk about that today because we're out of time. But that will be the next, I guess the things that we still have to do before the exam is we're going to deal with not ideal turbines and pumps. And then we're going to start to look at what we call Rankine cycles. But Rankine cycles are really just this 4-component system. At least what we'll do before the exam are the same 4-component system that we analyzed in class today. I will stick around if anybody has any questions, but if not, that's all I have for you today. Thanks, everyone.
Thank you, Professor.
No problem.
One thing about the homework.
Yep.
I noticed that in the syllabus, it included problems 6.8 and 6.82.
Yeah.
And I didn't see those in the 2 through 10 document.
6.8 and 6.82.
Yes.
Okay, I will look them up and figure out which ones those are supposed to be.
Okay.
And yeah, so then I'll send out an announcement about that too.
Okay. Every other problem was in the the document.
I probably just didn't update those ones because I looked too and I thought that I got them all, but it looks like I missed at least 2 of them.
Okay. The thing is, so there weren't any questions in between
those.
In between those that would have been the same as 6.8 and 6.82.
Okay. So I'll check it out and send out an email. Okay. It may be that I doubled something up, including the old numbers and the new numbers.
Okay.
Or it could be that, they often don't make big changes to textbooks, but they may have, sometimes it's, let's talk about this topic in a different chapter. So, but I'll check it out to make sure. So I really appreciate that, Dan. It helps me keep on track when you bring these things up. So I do appreciate you taking the time to do that.
All right. Thank you very much.
Yep, no problem. Have a good one.
You too.